Alright, so last week I didn't really know about work and didn't really know about energy, so yeah, the previous screencast was quite bad. But anyways, so to summarize this week, what we learned this week, basically we start off with the same, oh my god, we start off with the same equation as before, Jesus, work equals F times, oh my god, times, better, okay, never mind, redraw this, F times, but we also learned several other formulas. For example, work equals half of mass times V of F squared minus V of I squared, aka final velocity minus initial velocity. We also learned about these things, these charts, which are actually extremely useful. If you guys didn't really use it, I strongly suggest that you guys use it. So basically, K of I plus U G of I plus U, okay, that's not U, U S of I plus work equals let's see, what color should I use? I use blue. Okay, so K of F plus U G of F plus U S of F plus delta U I and T. So basically the initial loss, the initial kinetic energy plus the what's it again? Plus the gravitational potential initial energy plus the initial spring energy plus the work equals the final kinetic energy plus the initial, well, the final potential gravitational potential energy, the final spring potential energy, and the final, basically, it's kind of like heat, this structure. It's kind of hard to define. Alright, so oh right, I forgot about this. I went on a tangent here. But this is extremely useful as you guys use it. You can just cross out anything that you don't need. For example, if a book is falling, you only need these two and this one, not this. Well, yes, this. Well, this, but not this or this. If that's before the impact. If it's after impact, then you would need this. So nope. Okay, get rid of these things. Okay, so this is a formula for work, but this is a specific type of work. This is kinetic work, or if it's inside the system, this is kinetic energy. So let's draw, let's say, delta K, delta of the kinetic energy equals, oh, this stuff just comes out here. And then we learn about this thing, which is, so let's use red. Actually, no, let's use this color. So that looks no different. Let's call that U G, well, delta gravitational potential energy basically equals mass times gravity multiplied by h of F minus h of I, which is quite self-explanatory, to be honest. This one not so much, but this one extremely self-explanatory. Force displacement. And today we also learned about another one, which if you don't want it to be spoiled, stop the video here. But if you do want to see how you get, continue. So basically, delta U of spring is equal to well, we actually use, what was the constant we used? We used K. Kind of strange in my opinion, but sure. K times delta D squared and multiplied by 1/2. Now, okay, I'm going to do a proof right here. So we've seen in class that the relationship between force, so let's call this force, and the displacement is a linear one. That's a line, okay. And then, so I hope you guys see what I'm doing here. So then we basically use calculus to, this is very basic calculus. Do you guys remember the ones that we did for W of F equals a t half of at squared plus b of 0t plus, oh my god, what did I do? Make this x of f plus x of o. That was horrible. This follows a similar format. Basically force multiplied by, so basically this is the area of f times d. And this is a triangle, we can conclude that d times f times 1/2 equals the work. Now then, f, we remember, is k times d. So you substitute this in, and you get this equation. The delta is just like, it's basically initial and final. Alright, so now that we have all these concepts down, let's move on to a sample question I found in the textbook. Alright, note that I'll be using all variables here, so the actual problem isn't exactly like this. So let's say we have an object of mass m, and it's dropping onto a spring. It's dropping onto a horribly made spring, but good enough. Let's say good enough, but it's a spring, okay? It's a spring with a spring coefficient of k. So what we're trying to find is, when does the ball stop? Also, the spring has a height of h1, and the entire height is h, and the distance that we're trying to find, let's just call it d. So d is the distance that the ball will fall down onto, like, is how far the ball will basically force the spring to contract. So let's draw before and after. Okay, horrible. So let's see what forces are actually in use here. Oh, well, let's just go straight to it. To this. Back in a sec. Alright, so we have this equation. Since there's no force acting on the spring right now, this is 0. And this is also 0. But this is, I'm going to use right here. This, however, has a value. I'm not going to get that value yet, but okay, horrible coloring skills. Let's see if this closed. Alright, paint bucket. Go do your job. Oh my god, no. Alright, give me a sec. Brush. Does that work? No? Let's get up. Cap off. Alright, let's go. Yay, okay. Now then, let's see, I'll use yellow for this one. So basically all energy, so basically for this part, there's still no kinetic energy, because the farthest it goes down, at the point it's farthest down, it has no velocity. We cannot picture that, right? Because all the work is being transferred all the energy is being transferred into the spring, so there's none left for the kinetic. Gravitational potential, there's a bit, not as much as before, but there certainly is a bit. And then we have this, not that high, and I'm going to color these again. Hopefully this all goes well. Check that and go. Yay! Okay. All right. So this is what we have. U G of I is equal to U G of F plus U S of F. Now then, let's see what components UG, the initial gravitational potential energy is. So it's basically just the height. it's basically just m times g times h, which is equal to m times g. Now the height here is actually h1 minus d, which we cannot clearly see, I suppose. h1 minus d. And then you add on us of the spring potential energy, which is half d squared times k. Alright, now we have ourselves an equation. We know this value, know this value, know this, know this, know this, know this, know this, well, that's a number, know this, know this. So the only thing we're trying to find, oh wait, actually no. We don't know this, we know this, and so what we're trying to find is d. Now that, what we should probably do is basically set up, we can take this over here and use the quadratic formula. So I'll be back in a second. And so yeah, d equals this. You can pause it right now to see my work if you want. It's not exactly that difficult. It's basically just basic algebra and the quadratic formula. So this, well, it doesn't exactly encompass everything, but there is a second part of this question which asks you to find the point at which the object is as max velocity, which does involve all the concepts. So I suggested that you guys try that question. It's in the book. It's in the back section. I forget which question it was, but it's a decent question. It's a harder question, but it's a fun question. So thank you for watching, and I'll try to get the other one taken down. Okay.